Hello everyone and welcome to lecture today. Today we'll be talking about an introduction to proofs and generalizing different methods for dealing with proofs in logic and mathematics. Specifically, what we'll be discussing is the best way of proving statements within given what are called axiomatic systems, which form the basis and foundation for any different mathematical idea that you might have or want to prove. The first main axiomatic system that we'll define later in the next few lectures is called Axiomatic Set Theory. Before we do this, we want to go through and discuss different ways that we'll be proving things in this course and different methods that we'll be using in regards to the last lecture, which discussed logical rules of implication. So here we are with Introduction to Proofs. The main idea in any proof is to use the various rules of inference we discussed last lecture to chain together valid logical arguments within an axiomatic system. And the idea here is that if you have a given theorem that you're trying to prove within an axiomatic system, this is essentially what the process of proving something breaks down to. Is to combine the rules of inference in a coherent logical manner that kind of give a step-by-step proof of the theorem that you're trying to show or justify. In terms of general categories of proofs, there are typically two different ways of approaching a proof. For these two, we'll say, main categories, we have what are called indirect proofs, which are also sometimes called non-constructive proofs. And on the other side of this, we have what are called direct proofs, which are very often, what are called constructive proofs. A non-constructive proof is a proof that uses already established, well-established mathematical ideas and combines that with different interesting parts or pieces of logic to indirectly prove something. So we'll say an indirect proof is a proof which uses well-established mathematical ideas or constructions as well as logical equivalences to go through and prove a given theorem or a new theorem in mathematics. The most common example of an indirect proof method is called the proof by contradiction, and we'll see how to go through and, logically speaking, why proof by contradiction works. But the idea is that this will be a very common method of proof that we'll see in this course, and that you will see in many different areas of mathematics. Whereas a direct proof or a constructive proof uses new mathematics or mathematical ideas, say new mathematical ideas and constructions, to go through and logically prove a given statement in mathematics, a statement or theorem. The main difference between these two proof methods is that with the direct proof, we'll see that we end up constructing new mathematical objects, new mathematical sets. When we start talking about axiomatic set theory and using sets, the idea of sets to prove things, when we define axiomatic set theory, this will essentially be a construction coming directly from our logical axioms, and we'll be forming our own what's called axiomatic system. But this is the main difference between a constructive proof and a non-constructive proof in mathematics. We'll focus first on proof by contradiction, and then go through and show directly what the logical basis is for a proof by contradiction. So to logically justify and explain proof by contradiction, we want to go through and think about what the logical basis is for a proof by contradiction. And the idea is that it's purely based on the following idea. We want to show that a given proposition P is true. The idea is that if we can derive a contradiction, and we'll call this contradiction Q, this is a statement that always evaluates to false, such that we have the implication not P implies Q is a tautology, so is always true. So this statement not P implies Q is a tautology, then logically P is also a tautology, or also always true. And the reason for this is a relatively simple justification. Well, we have that if we can show that there exists some contradiction Q such that not P, the implication not P to Q is true, then we know that this implication will always be logically equivalent to not P or Q, which is a tautology, and not P, the double negation of P, is in fact logically equivalent to P. So we have that P or Q is always true. And because Q is a contradiction, or always a false statement, this is the same thing as P or F being a tautology. And one of the main logical equivalences that we have is that, if you remember, P or F, this is the same thing as the truth value of P. So because P or F, P or the or statement with any proposition and a contradiction is just going to be always the same as the truth value of that statement. We've effectively shown that P must in fact be a tautology. So the key thing for proof by contradiction is this step, deriving a contradiction. This can be any contradiction, but you need to derive a contradiction such that the opposite of what you're trying to prove implies this contradiction, or gives you this contradiction, and that is always a tautology. This is the logical basis for any proof by contradiction. For our first example, we'll start with one of the most common proofs in mathematics, which is to see that the proof that the square root of 2 is an irrational number. So we're trying to prove the proposition that square root of 2 is an irrational number. This is our statement P that we're trying to prove. And the idea, just like we talked about in the motivation, we talked about the motivation of why proof by contradiction works. We need to try, so to try and prove P, we must show that assuming the opposite statement, or not P, leads to contradiction. So the proof is going to be done as follows. We first assume not P, or the statement that the square root of 2 is a rational number, and we need to derive a contradiction. And the first thing that we're going to do is go through and deconstruct this, deconstruct what it means to have the square root of 2 be a rational number. So if the square root of 2 is a rational number, that means that there exists an integer a and a positive integer b, such that the square root of 2 can be written as a over b, and this is one of the key points, the integers a and b are in lowest terms. So what this lowest terms means is that the greatest common divisor of these two numbers, these two integers, is 1. And just simply put, you should hopefully remember this from a high school mathematics course, or even grade school mathematics course. For any two fractions, say for example the fraction 6 over 27, this fraction is not in lowest terms because 6 is the same thing as 2 times 3, and 27 is the same thing as 3 times 9. So this fraction 6 over 27 is not written in lowest terms. The fraction 2 over 9, though, is written in lowest terms. So the idea is that this is directly of great importance in this proof by contradiction, because it turns out that this is the statement that we end up getting a contradiction. We end up actually contradicting when we assume that the square root of 2 is a rational number. And we do this as follows. So if this is true, then we have that the square root of 2 is equal to a over b. It can be written as a over b, which is in fact the same thing as a being equal to the square root of 2 times b, or a squared being equal to 2 times b squared. Now, this is a very interesting statement because this is actually a statement that's telling us that a squared is even. And this is because any even integer is going to be expressible as 2 times m for some m. So because a is 2 times b squared, this is just saying that a squared is equal to 2 times b squared. This is just saying that a squared is equal to 2 times m for some integer m, and therefore a squared is even. The next part of the proof is going to be that, well, because a squared is even, we want to see what we can figure out from this statement. So if a squared is even, what do we know from this? And it turns out that we actually have, you could call this a little lemma, that for any integer, if a squared is even, then the integer a must also be even. And you can show this using a proof by cases. It's a relatively straightforward proof by cases, because you only have two options, that an integer is even or an integer is odd. And if you go through and essentially test this, check this for odd integers versus even integers, you'll see that any odd integer squared will also be odd, and any even integer squared will also be even. So we can maybe do this on the side over here. So if a given integer, we'll call it a, is odd, then a can be expressed as 2i plus 1, and therefore a squared will be 2i plus 1 squared, which means that a squared is going to be equal to 4i squared plus 4i plus 1, which is the same thing as 2 times 2i squared plus 2i plus 1, or 2 times n plus 1 for some integer n, which is the definition of an odd number. So this is essentially showing us that for odd integers, the square of an odd integer will always be odd, and furthermore, you have that the exact same result for even integers. If you go through and do this process for an even integer, then for an even integer, a can be written as, say, 2 times I, which gives that a squared is going to be 4 times I squared, and then it's the same thing as saying that a squared is equal to 2 times 2i squared, or that a squared is equal to 2 times m for some integer m. So the main idea here is that for any even integer squared, you'll also have that the square of any even integer will also be even. Therefore, with this proof by cases, we have that we can use this, that we've shown that a squared is even, therefore a must be even, and this will lead us to then that a has to be equal to 2 times m for some integer m. But if this is true, remember that a is equal to the square root of 2 times b, and a squared is equal to 2 times b squared because of this. So then a squared is equal to 2 times b squared is the same thing as saying 2 times m squared is equal to 2 times b squared, which give us that 4 times m squared must be equal to 2 times b squared, which finally lead us to the equation that 2 times m squared has to be equal to b squared, which gives us that b squared is an even number. And directly due to the previous lemma, this implies that b is an even number, which is the same thing as saying that there exists an integer, we'll call it p, such that b is equal to 2 times p. And we'll stop here and look back through the proof and see if we have derived a contradiction. And sure enough, we have derived a contradiction. I think for a little bit about where exactly this contradiction is, but the contradiction is essentially going to be should be directly present here, and it is directly present. The main thing I mentioned it earlier, it has to do with the GCD, right? We assumed initially that the square root of 2 is a rational number, and therefore it can be written as this ratio of a over b, where a is an integer, b is a positive integer, and this ratio is in lowest terms. So the greatest common divisor of these two values is 1. Right? This a and b are chosen so that this is the case. But we've proven that if this assumption is true, then a is even, a must be even, and b must be even. So if a is even, then a is equal to 2 times m for some m, and b is equal to 2 times p for some p. Right? So this is essentially giving us that the greatest common divisor of these two integers, a and b, is 2, not 1, which is it's definitely not consistent with what we assume, which is that the greatest common divisor of a and b is 1, or that fraction is in lowest common lowest terms. So this is a contradiction. We've successfully derived a contradiction by assuming the statement, the opposite of what we're trying to show, which is the square root of 2 is a rational number. So therefore, we must conclude that the square root of 2 is not a rational number, or that the square root of 2 is an irrational number. So this is a relatively common proof, and it's a very good proof for showing exactly how to do a proof by contradiction in mathematics. So the next proof method that we'll talk about will be a direct result of the previous proof that we discussed, and this will be a proof that is another example of a non-constructive proof. So it's not going to be a proof by contradiction, but it's going to be an example of a non-constructive existence proof. And this will be a proof of the statement that there exist two irrational real numbers, we'll call these x and y, such that x raised to the power of y is a rational number. And the proof of this relies heavily on the fact that the square root of 2 is an irrational number, which we proved in the previous example, and it also relies on essentially what's known as a proof by cases, similar to the proof by cases we did for the lemma in the proof of the previous statement. And the main axioms that we're going to use in the proof is the following. We know that the square root of 2 is irrational, and we're going to use the definition of the number, we'll call it z, square root of 2 raised to the power square root of 2. Now, we know that z is a real number, and therefore is either rational or irrational. So we have two separate cases that we need to consider. Case number 1 being, if z is rational, then we are done, because x here is the square root of 2, y we choose as the square root of 2, both of which are irrational numbers. And if then x to the y is rational, then we're done. Now notice, we don't know if this is the case. I haven't proven, right, that this is the case. And it turns out that this is actually not the case. But a proof by cases really is just going through and investigating every single possible case present and showing that the statement is true for each individual possible case in each individual possible case. So case number 2 is if z is an irrational number, in which case we have to think a little bit more closely about exactly what we need to choose for our x and our y. Specifically, we can choose x to be equal to z, or square root of 2 raised to the power square root of 2, and y to be equal to the number square root of 2, in which case x to the power y is equal to the square root of 2 to the power square root of 2, which is z, raised to the power y, which is square root of 2, which is equal to the square root of 2 raised to the power square root of 2 times square root of 2, which is the square root of 2 squared, or 2. So x to the power y is just equal to the rational number 2 over 1, and therefore it is rational. And this concludes the proof in this example, because we've shown by cases, regardless of whether z is a rational number or an irrational number, in both cases you can find an x and a y that makes x to the y rational, or turns it into a rational number. Now it turns out that case 2 here is in fact the correct case, and it turns out that the square root of 2 to the power square root of 2 is in fact and can be shown to be an irrational number. This is called the Gelfand-Sneijder theorem. But we don't actually have to know this theorem to do the proof by cases in this case. This is a good example of a non-constructive existence proof, because we're not building any new mathematics, but we're just using a proof by cases and what we know about mathematics in the real numbers. In the next lecture, we'll see how to construct what's called an axiomatic system, as well as how axiomatic systems are essentially the basis for any and all mathematical constructions and mathematical theorems. So we've seen a number of different examples today of how to do non-constructive proofs, and we'll see as we build up the mathematical ideas in this class that you can typically prove things in a better manner using what are called direct proofs or direct constructions in mathematics. And this involves what are called building axiomatic systems, the main example of which is going to be axiomatic set theory, which is the next main topic that we'll be discussing. Thank you very much for tuning into the lecture today, and I hope you had a great day.